Hey guys, this is Saptarshi here and welcome to our YouTube channel. Last few video tutorials we are discussing about CNN architecture. We've already looked at how LeNet 5 and AlexNet works. So if you're interested, you can quickly take a look at our playlist. Today we are going to discuss about another important CNN architecture named as VGGNet. So let's do a quick recap. CNN really established itself with this LeNet 5 architecture proposed by legends like Jan LeCun and Joshua Bengio. So this came around 1998 and established itself on this dataset named as MNIST, right? So this is the hello world for computer vision datasets where you have these handwritten digits, okay? It took, however, quite a lot of time to establish itself as a front runner in this computer vision classification task. Okay, so for that, one of the data set which was very important is known as ImageNet. Okay, so let's look at first the architecture of LeNet 5 and AlexNet quickly, and also why the computer vision community is so much excited, so much gaga about this ImageNet dataset. Okay, so if you look at the left side, so this is your LeNet 5, okay, and this is your AlexNet architecture. So at a first go, like any CNN architecture, both has this feature extraction layer and this classification layer. Both have this. However, the AlexNet has a much deeper feature extraction layer, so it can actually find out more useful, more complex features. And if you look at the final layer, fully connected layers, though the number of layers or number of components are same, but look at the last layer. So here you have only 10 nodes in the final final fully connected layer, because it is a 10 class classification problem. And look at the other one. So that's where we are focusing on ImageNet. So if you look at ImageNet and compare with other test bed of images that were there, so look at MNIST over here, it had 10 classes, right? So you have number of classes in y-axis and number of data samples in x-axis. So ImageNet actually is a class away from all other image data sets, and that's the reason when AlexNet proved its supremacy on ImageNet, then people started taking CNN more seriously, and that's when more and more architectures has come up. Okay, so in 2014 competition of same ImageNet, Karen and Andrew of Visual Geometry Group of Oxford University proposed a family of convolutional names. All right, and this proposed architecture actually obtained the first and second place in two tasks. One is the localization task and another was the classification task. Okay, so today we are going to focus more on this VGGNet. As I said that it is a family of convnets, so they actually used 6 architectures or 6 configurations. Okay, and each one had different number of weight layers or something or other was changed. So let's go one by one. So first convolution layer had 11 weight layers. So weight layers are actually the pooling layers are not weight layers, and you have these fully connected layers. Okay, so these are also your weight layers. So if you count 1, 2, 3, 4, 5, 6, 7, 8, and then these 3 layers, so you have this total 11 layers. Okay, LRN actually had again 11 weight layers. And if you remember, one of the things that AlexNet proposed for this local inhibition, right? So which was normalization, but at a much greater scale, which was known as LRN. Okay, so they wanted to compare that if we apply LRN in any of the units, does our performance improve or not, right? And then in the next layer there were more convolution layers which were added. So it was 13 weight layers, right? So here one of the things that happened in this layer C, which has 16 weight layers, was that there was a convolution layer which was one dimensional. Okay, so this was an interesting experiment they did. So one dimensional convolution will actually not do anything with the shape of the feature maps, right? Or anything with the spatial configuration of the image, but it will just add a layer of nonlinearity. Okay, and layer D has 16 weight layers, but now this is a full formed convolution layer. So this has the 16 weight layer, and E has 19 weight layers. Okay, so these are all called as VGG nets. However, the famous ones which you see in the literature are these two, D and D, which are actually appended with this letter VGG based on the group they are working from, right? So these architectures are known as VGG 16 and VGG 19. So a quick recap. So compared to AlexNet, right, we have more layers. Another thing that is important is that now we are stacking more convolutional layers, right? So though in LeNet 5 there was a convolution layer, then a pooling layer, so they were kind of alternating. In AlexNet, it was not alternating like this. So initially it was alternating, then there were 3 convolution layers and a pooling layer. Here you have more of that repeated. Okay, so there is a block where you have 2 convolution layers back to back, then a pooling layer, again a 2 block, and then a block of 4, and so on and so forth. Okay, now look at how these are denoted. Okay, so if you look at any of the convolution layers, it is written like, if you look at this one, conv 364. So what does this mean? So this means that in this layer, the filter size is 3 into 3. Okay, so the filter size that we are applying is 3 into 3. And how many filters or how many channels we are applying? We are applying 64 channels. Okay, so let's understand with another example. So if you look at conv 3512, so this is also a 3 into 3 filter, and there are 512 filters like this. So one of the things that we notice over here is that we are considerably using smaller sized filters, right? So we have used earlier 11 into 11 or 5 into 5 and so on and so forth. Here we are using 3 into 3, and not only that, for the entire architecture, all of them has 3 into 3 convolution. Okay. All right. So we'll take a quick recap of how this convolution operation works before understanding why the smaller sized filters have a better chance. Okay, so in terms of parameters, this A and ALRN actually had 133 million parameters. So these are in all millions. Okay, and gradually the parameters have increased. And if you remember AlexNet's parameters, so they were 62 million, right? So it has increased quite dramatically if you look at that. Okay, all right. Now let's look at the convolution operation. So you will typically look at a portion of the image which will be multiplied by something called as a filter. So this is a 3 by 3 filter which will actually sit like this, okay, in a 3 into 3 position, and then there will be an element wise operation, and this element will actually correspond, the middle element will correspond to this. So it will gradually be of reduced size, and there was also something called as a stride. One important thing or one confusion that I often come across students is that when I have multiple channels, so that may be channels because of this red, green, blue, that may be channels because of number of convolution or filter operations, how they actually give me something like this, right? So what happens over here is, if you consider these as 3 channels, right? So these 3 filters actually apply on 3 channels, and you get this activation map, which are now aggregated. Okay, so this aggregation happens, and that's how you get the final output from your convolution layer. Okay, now why a smaller size kernel would work? Okay, so let's understand this. So let's take an image which is a 5 by 5 size, okay, and a kernel of 3 by 3 size with a stride of 1. So if I do like that, right, so what will happen is, right, so I'll start from here, right, so this middle element will go over here, right, the convolve operation, then I will take a stride of 1 and so on and so forth. So my kernel size will actually become 3 into 3. Now again, if I apply a 3 into 3 convolution on that, so what we are trying to explain is that what happens, we stack 2 3 into 3 convolutions, so we get a single number because this is the same size as the 3 by 3 kernel. So take a little bit pause and think that what is the effect that is happening if I am stacking two 3 by 3 convolution layers. So it is actually having the effect of a 5 into 5 convolution layer, because you know the initial image was 5 into 5 and you are just getting one value out of it. Okay, so that's one of the things and how it helps. Okay, so not only that, we have two 3 into 3 kernels, but as I have two layers of convolution, you have multiple layers of nonlinearity. And you know that why neural networks are so good is because they have this capability of finding nonlinear features, right? So this is one of the most unique points. And using two convolution layers, you have more possibility of adding nonlinearity. So actually, if you stack 3 into 3 kernels in 3 layers, right? So it is equivalent to a 7 into 7 kernel. Okay. Now, is there an advantage in terms of number of parameters? So if it is a 7 into 7 kernel, then the number of parameters are actually a function of 49, because you know all these 49 values that you have for the 7 into 7 kernel, right? So that will be needs to be determined, and that is a function of the number of parameters, or a function of this number 49 and number of channels. Whereas if I use a 3 into 3 channel and we use it 3 times, then it is a function of this number 3 into 3. So this is for one convolution layer. You have 3 layers stacked, so you actually need 9 plus 9 plus 9, or 9 into 3, so 27, and number of channels. So if you compare with respect to 27 and 49, so 49 is actually 81% more parameters. Okay, so that is one of the, or if you have to actually tell, one of the important or striking distinction with AlexNet, that will be smaller and uniform kernel size. Okay, so this now is about the results. Okay, and if you look at this is still compared with this top 1 validation error and top 5 validation error. So top 1 is that you are correct, you are predicting that image level correctly, and top 5 is that you are predicting the top 5 labels, and it do not fall even in the top 5. So that is your top 5 validation error. Okay, and you see that there is interesting thing. So why they actually didn't use LRN later is that when they introduced LRN, actually you see that there is no improvement, and LRN of course needs more computation, right? And when they brought in B, that is added more layers, it improved. Okay, and then when they brought in C, okay, where actually you use the 1D convolution, there was an improvement, but it is not a lot of improvement. So it is better to use normal 2D convolutions. Okay, and you see that it actually step by step, this E actually gives the best result. There is one more thing on the test setup which I will draw your attention to, is something called as scaling. So they actually took the same image and scaled in a different manner, right? So they stepped it up, stepped it down, right? Increased it, decreased it, and trained it. So they did it for both test and train. So this they called as jitters, and that made the CNNs probably better in their performance. So this is also one of the things which is striking for VGGNet when you talk about setting up the experiment. Okay, and they finally, as they had this family of nets, so it is obvious that they tried some kind of fusion techniques. Okay, on top of it, so combine the results, and you can see that the results actually further improved. So it was 8 in this case, and when you applied a fusion, it went down to 7.3. So that's kind of brings us to the closer of our VGGNet discussion. I hope you have found something useful over here. Thanks so much for watching this video, and we would love to hear from you. We'd love to get your feedback and comments, uh, and actually talk to you and know how you liked our video. Okay, thank you so much.